we testing next week for this?
Alrighty. So now that you know how to draw compounds and determine shape, there are a few other things we want to be able to do with them. One is polarity. Now, you know from last year that you can figure out whether a bond is polar based on differences in electronegativity. Chlorine is more electronegative than hydrogen. It will draw the electrons in this bond toward it, and you have a dipole in which the chlorine has a partial negative charge and the hydrogen has a partial positive charge. You've seen water drawn out for years in its bent structure. You know that water is a polar molecule. That's why you can't use it to clean oil off something. Oil is nonpolar, water is polar, likes dissolve likes. We'll get into that in much more detail, much more chemical detail shortly. Oxygen is more electronegative. You know each of these bonds is polar, and there is a net dipole overall moving in this direction. So you've got partial positive amongst the hydrogens, partial negative on the oxygen. So this is a polar covalent molecule. Couple things I just want to show you in case you see it written this way. I don't think it will bother you. A dipole moment essentially is just the product of the magnitude of the charges and the distance that separates that positive and negative charge. They may give you dipole moments. They'll give you actual quantities. This represents a dipole moment. The unit is debye. You don't need to know how it comes to be. Polar molecules don't have dipole moments. Polar molecules do have dipole moments. They are non-zero dipole moments. Non-polar molecules do not have dipole moments, and that's why the dipole moment will be zero. So polar does, non-polar doesn't. What we want to look at is whether a molecule is polar or non-polar. You can figure out whether bonds are polar. Anything that hooks to fluorine that is a nonmetal will be polar. A C to H bond, as I said the other day, this is a nonpolar covalent bond. That's a good one to know. Typically, the way you figure out if a molecule is polar or nonpolar is to determine its shape and look at whether it's symmetrical. Let's take several examples. In C, it says a molecule with all nonpolar bonds and no lone pairs of electrons on the central atom is nonpolar covalent. And again, this you should have seen in honors. Methane. The C to H bond is nonpolar covalent. You have all nonpolar covalent bonds, no lone pairs on the central molecule, on the central atom, and the molecule is nonpolar covalent. All the bonds are nonpolar. D says if only one bond is polar, the molecule is polar, and that's because the molecule is asymmetric. For example, if you had methyl fluoride, it's going to look very similar, tetrahedral shape, but any nonmetal hooking to fluorine will result in a polar bond. There's your dipole right there pointing toward the fluorine away from the carbon. This is a polar covalent bond. You have one polar covalent bond, all others are nonpolar covalent, and as a result, this molecule is polar covalent.
How do you know that that's
anything that hooks to fluorine that's a nonmetal will be polar. Fluorine's electronegativity is so much higher than everybody else, it'll be polar.
So is the C to H still nonpolar?
Absolutely. Well, these bonds are nonpolar, but the molecule is polar. Now, if you had an F here and an F here, the molecule would still be polar covalent because these are not straight across, right? You have angles of 109.5, so don't be confused there.
What if it was tetrahedral? Like, can you have a tetrahedral with a polar? Or
I know what you're going to ask, and the answer is yes. Let me get there. It says the presence of a single. Go ahead, Maddie.
sorry, you said that a non-metal that bonds to fluorine?
Will always be a polar covalent bond. The presence of a single lone pair of electrons on the central atom results in a polar molecule because the molecule is asymmetric. This is the one you would have seen last year. Now it turns out that this bond is polar covalent, but it doesn't even matter. If you have a single lone pair of electrons on the central atom, the molecule is going to be polar covalent because the molecule is asymmetric. So in this case, the molecule is polar covalent because of its asymmetric structure. Same thing there. And I think where you were going, Faith, is where something else you would have seen last year. It says if all the bonds are polar, examine the shape to determine whether the dipoles cancel. Yeah. If they cancel and there are no lone pairs on the central atom, the molecule is nonpolar. The example you would have seen in honors would be right here. What?
I was going to go back to the other one. How do you know that the nitrogen to hydrogen is polar covalent?
You probably might not be able to guess unless they gave you electronegativity values. I'm a geek, so I know all of them, and or most of them, so I know this is a polar. But I also know ammonia is a polar covalent molecule.
It's anything above 0.5.
Right? 5, yeah. Well, 0.5 and up. And then here, I think this is your question, Faith. I think this is what you were thinking about. You've got a dipole, you've got a dipole, you've got a dipole, you've got a dipole. This is like only in the movies, okay? Let's say you have a dead body on the floor and some gangsters need to move him out really quickly. And this is like 4 people of equal size, weight, height, etc. picking up the dead body. One picks up an arm, the other picks up an arm, one picks up a leg, one picks up a leg. And they all try and move in opposite directions at the same time. They just cancel each other out. Probably not the greatest example, but maybe if 4 little kids were fighting over a Tinker toy with 4 sticks in it and they each tried to pull at the same time, the sticks would just come out and down it would fall. Same basic concept. So this one is interesting because these bonds are all polar covalent. However, the molecule is nonpolar covalent because the dipoles cancel due to perfect symmetry. And you'll note the spelling with symmetry, 2 M's in symmetry, and asymmetric. It doesn't start with ass, okay? It's just A-S. It's A for not, so it's asymmetric. I'm just trying to help you with your spelling. Now, yes?
Why isn't it asymmetrical?
It can be asymmetrical depending on what your set and structure is. But it can be asymmetric structure because if it's asymmetrical structure, that'd be fine. I don't know. We better run it by Detman. I'll check. In any event, what I do want to mention is what's written in blue. There's actually nothing here that you didn't learn in honors or should have learned in honors. But here's the kicker. It says be very careful with linear. This is 2 atoms attached, 3 lone pairs, and square planar, 4 atoms attached, 2 lone pairs. Because these are symmetric, so they can be nonpolar. Be careful with those 2. They are tricky-wicky. Let's take a look at all of these examples which we've drawn out, and that'll make it easier.
Wait, how is it symmetric if there are 3 lone pairs?
Because the lone pairs are in equatorial direction, so it's up that way and that way. So they cancel.
Okay.
Yeah, we're going to hit all of those. Doesn't matter.
What does the A mean again?
The A is the central atom, X is the terminal, how many lone pair, how many lone pair?
Lone pairs on there.
Central. All right, so if you have nitrogen, anytime you hook to yourself, it's going to be what type of molecule? Nonpolar covalent, no difference in electronegativity. All right, methane we already did. That one's right here, CH4, you know is going to be what? Nonpolar covalent. You have all nonpolar bonds. Nonpolar covalent. We've got boron, trifluoride right here. Faith, what are you going to guess?
Okay.
Fluorine to any nonmetal is going to be what type of bond?
Polar covalent, but they're not equidistant. It was a different word.
Well, they're in equatorial directions, but make it simple for yourself. Is the molecule symmetrical?
Yes.
Yes.
The dipoles cancel.
Yes, exactly. So this is a nonpolar covalent compound because it's a symmetric or symmetrical structure and the dipoles cancel. Sulfur dioxide right here would be polar covalent. A lone pair of electrons on the central atom, a 1 lone pair, automatically polar covalent. Here, the molecule's asymmetrical, the dipoles don't cancel. We have xenon tetrafluoride. Where's that one? I got it. Right here. What do you think? Careful.
No, nonpolar.
That's a nonpolar covalent. This one is such that these dipoles will cancel one another out, as will these. So this is in a square linear fashion, and as a result, the dipoles do cancel. When I say square linear, I really mean planar. What about sulfur hexafluoride? Nonpolar covalent, symmetric structure, dipoles cancel. And this is the other funky wonk. What about this guy? Nonpolar covalent, because it's symmetrical, you've got it. Dipoles cancel.
What about the bromine pentafluoride?
Bromine pentafluoride, what's its shape? Is that trigonal bipyramidal?
Yeah. No,
That's-
octahedral.
Which,
Square.
do you mean with the ion? Do you mean
It was
the one we drew before the break?
No.
No.
Okay, but this is a really good question. Hang on. Tell me why this is neither nonpolar nor polar covalent. Because it's an ion. Careful, careful. But you mean this one?
I can't see. But yes, that one.
Why does that have to be polar covalent?
Because it's asymmetric.
You have a lone pair of electrons on the central atom. It's therefore asymmetric.
Okay.
Polar covalent. Good. Couple more things I want to take a look at, and I'm going to make this really, really, really simple. We know that electrons are in orbitals. When atoms get close together, those atomic orbitals can overlap to form molecular orbitals. And rather than just have S or P, we tend to get a blending of the orbitals. And these are going to be hybrids. I'm going to keep it really, really simple. Really simple. Like all this stuff, we'll just cut right to the chase. Molecular geometry is determined not only by the shapes, but also the orientation of these hybrid orbitals. You know you have S, and you can have 3 P's. Well, an S can blend with a P, or an S can blend with 2 P's, or an S can blend with 3 P's. And you get what's known as a hybrid orbital. We're only going to look at 3 hybrid orbitals. I promise this is going to be so easy. SP is when you blend 1 S and 1 P, and you'll see this for any structure with linear electron group geometry. SP2 is 1 S and 2 P's. You'll see it with double bonds. Sometimes. And you'll see it with trigonal planar electron group geometry. SP3, 1s, 3 Ps. You'll see this for tetrahedral electron group geometry and for single bonds. You are no longer responsible for that type of hybridization, so we're going to keep it very simple. Let me show you how to do this. Super easy. With 2 electron groups, for example, you could have either of these structures, the beryllium or the carbon is attached to 2 atoms, no lone pairs. The number of electron groups is 2 plus 0 is 2. When you have 2 electron groups, your hybridization is SP. And that's because S1, P1, or 1 plus 1 is 2. Bear with it for a minute and you'll see it. Let's say, for example, you had boron trifluoride, or sulfur dioxide. The other example is the same as the first. You have 3 atoms attached, no lone pairs. What do you have on the sulfur? 2N, 1. How many electron groups? 3. You have hybridization, SP2. You have S1, P2. 1 plus 2 is 3. And let's look at the last type. Let's say you have tetrahedral, or you could have trigonal pyramidal, or you could have bent, and what is the total number of electron groups in each of these? 4. What's your hybridization? sp3, because S1, P3, 1 plus 3 is 4. And that's as much as you need to know about hybridization. I'm sorry. That's right. Here's the last piece of the puzzle. Last piece of the puzzle. And we'll review a few things on Monday, and I'll tell you what I expect over the weekend. Last piece of the puzzle. The way the bonds form is how the orbitals overlap. You don't really need to get into it very much. You either have sigma bonds or you have pi bonds. Single bonds are sigma, single, sigma. In a double bond, you have 1 sigma and 1 pi, and I'll show you what they look like next time. A triple bond has 1 sigma and 2 pi's. Take a look at this structure down here, which happens to be cocaine. Now,
Wait, hold on, let me copy that down.
I actually did that from last year. We had a whole conversation about it.
Oh yeah, and math.
all right,
And math.
guys, let's finish.
That's
Anytime you have a double bond, you have 1 sigma and 2 pi's. How many pi bonds in this structure? 1, 2, 3, 4, 5. 5 pi's.
Why are they so
Triple
long?
bond, we have a triple bond.
Take a look at this one here. Keep it simple. How many pi bonds? 1. How many sigmas? 1, 2. Go back to my fun little structure. Lone pairs are not shown here, but you know they exist. Look at this oxygen. It has 2 bonds, and it would have how many lone pairs? 2. Raise your hand and tell me, SP, SP2, or SP3? SP3, because it has 2 bonds, 2 lone pairs. 2 plus 2 is?
4.
Look at this N right here. What is the N missing? A lone pair. SP, SP2, or SP3? SP3 is correct. 4 electron groups. Wherever the lines meet, you have a carbon. This carbon is connected to 1, 2, 3 atoms. SP, SP2, SP3. SP2. You've got it. On your quiz, I gave you a simpler structure than this one, but I did it like this because it was easier than freehanding one, so I didn't want you to be confused. This is what I recommend over the weekend. The sigma pi thing is so easy, you're not going to have an issue with it. The hybridization you'll master in the lab. Please take the time in your POGL packet. This Properties of Covalent Bonds has a really nice piece on polar and nonpolar toward the end. Highly recommend that. We are going to be doing a lab in here on Monday where you will be constructing the compounds. The lab is on Edline, but if you want a copy, pick it up. You must have your table with structures drawn ready to go. If you didn't pick up your quiz, do so. For Monday, you want mastery of shapes, polarity, and as much as I showed you with hybridization, keep it very simple.